Atomically precise manufacturing is not being held back by imagination. It is being held back by verification, error correction, and throughput. In 2026, the core reality is simple. We can move and arrange atoms in constrained lab settings, but we cannot yet manufacture arbitrary, macroscopic, three-dimensional objects with atomic precision. No demonstrated workflow in this evidence base crosses that line. The gap is not a single missing invention. It is the coupling between atomic control, metrology, drift, contamination, and the economics of proving you got it right. A useful way to think about the field is that atomically precise manufacturing is not one technology. It is a family of bounded methods. Some rely on tip-based manipulation, like scanning probes that can push, pull, or position atoms on defined substrates. Others look more like chemistry, producing atom count-defined clusters, then trying to assemble them into larger, functional structures. Another track focuses on two-dimensional designed materials, where defects, dopants, edges, and interfaces can be controlled more tightly than in free-form, three-dimensional bulk. That boundedness matters for strategy. Atomic precision is most commercially defensible, where atomic arrangement directly controls function. Catalysts are an obvious example. So are optoelectronic nanostructures, sensitive interfaces in two-dimensional stacks, and high-value molecular or nanoscale intermediates. When one misplaced atom changes a reaction pathway or shifts an energy band, the value of control rises fast. The counterintuitive bottleneck is that moving atoms is not the hardest part. The hardest part is producing the same atomic configuration again, verifying it quickly, and doing both at useful yield. Atomic scale demonstrations are often overfit to a specific surface chemistry, a specific probe, or a specific device motif. To become manufacturing, the system must hold calibration, reject drift, stabilize the environment, and keep contamination from erasing the very precision you paid for. That is why the strongest scaling thesis treats atomically precise manufacturing as a platform engineering problem. Think closed-loop control, calibration routines, drift rejection, probe and tool design, environmental stabilization, automated verification, and software that can run the process repeatedly. In 2011, wireless embedded control concepts were already being discussed for these tools, signaling early recognition that distributed control architectures might matter at the atomic scale. By 2018, novel probes for tip-based approaches were reported, pushing on tooling rather than just one-off manipulation feats. In 2022, a platform framing was published that put mechatronics at the atomic scale at the center of any high-throughput path. Mechatronics might sound mundane next to visions of molecular assemblers, yet it is the point. If you cannot sense what happened, actuate precisely, and correct errors in real time, you do not have manufacturing. You have a delicate experiment. The research questions follow directly. How do you increase operation rate without losing placement accuracy, chemical selectivity, or verifiable yield? Which defects can be detected and repaired during fabrication, rather than discovered after? How do you certify atomic configuration faster and cheaper than exhaustively characterizing every output? Verification economics is where many roadmaps quietly fail. If every unit requires deep microscopy and expert interpretation, then the cost per verified atomic operation stays too high. So the real competition may be between measurement protocols and process complexity. Can you design verification thresholds that are auditable and fast, without being so lax that atomic precision becomes marketing language. A second high-impact finding is that chemistry may scale where manipulation does not. Atomically precise nanochemistry is now a reproducible domain with defined terminology, cluster classes, synthesis routes, and characterization concerns. Work published in 2023 consolidated introductions and synthesis constraints for atomically precise clusters, including noble metal clusters. A 2025 publication extended that literature towards self-assembly pathways, aiming to build larger structures from well-defined nanoscale units. That direction suggests a pragmatic route: package atomic definition into stable building blocks, then assemble those blocks rather than placing every atom individually. Still, cluster-to-device translation is not automatic. A cluster can be atomically defined in isolation and then lose structure or lose function when integrated into a catalyst support, a sensor surface, or a larger interface stack. So an investor-grade question is not, can we make the cluster? It is, does the cluster keep its identity, and does the system-level performance remain reproducible? Two-dimensional designed materials form another near-term wedge. Constraining geometry changes the game. In 2022, atomically precise manufacturing for two-dimensional designed materials was published, connecting atomic scale control to bounded architectures where configuration can be tied to device-relevant function. Here, controlling vacancies, dopants, edge structures, and interfaces can plausibly justify process development because a small set of atomic motifs can dominate performance. Governance belongs in the story earlier than most technologists prefer.